So next up, we have Ted Hua and Sayan Dasgupta from LinkedIn to talk about finding spam in small text fields. Thank you so much for coming. From Bangalore, actually. Sayan, welcome.
Hello. Hello? Okay. Hello, everyone. I would like to thank Facebook again for organizing this conference. It's great to see so many people working on spam and related problems. So my name is Ted Hua. This is Sayan Dasgupta. We're from the Security Data Science team at LinkedIn. And what we do is we do all of the abuse detection and prevention on the site in terms of anything from spam to scraping to fake account creation, to a lot of topics we've heard about in a lot of different talks today. And what I want to talk about in this talk is finding spam in small text fields. So it's small text fields. Okay. There we go. Okay. Wrong button. All right. So there are sort of two types of spam that I'm classified here in this slide. So one, what I call sort of direct spam. So direct spam is private messages, groups, places on a site where users are directly communicating with other users in terms of they're sending messages, they're posting messages to groups, and as opposed to indirect channels, which are profile data, is the typical example. So names, school, company, so places where you fill out your profile, but this information gets gets echoed to other users in specific content, in specific places, not usually because they asked for it, but the site displays it because it wants to show the name of the user or their company or so on. The typical case in the indirect spam channels are there words and short phrases. They're not paragraphs and sentences. So here's an example. So this is LinkedIn's Who's Viewed Your Profile. So now here, what I'm showing is a real person going to LinkedIn's Who's Viewed Your Profile, and it shows the name of the person who has viewed their profile. And in this case, you see, it just says spammer account. But you can imagine the spammer can put whatever they want in the name field there, and then the spam will show up. So now, admittedly, this is maybe not the most efficient spam vector because you have to view the profile of every person you want to target, and then you will only get the people who actually go to who's viewed your profile. But the problem like this can happen, right? And if users see this is annoying. So that's an example of an indirect spam channel. Here is another example, which is maybe even less obvious, which is you go to add a new email address to your account, right? And it's normal when you add a new email address for a site to ask you to confirm the email, right? They send you an email and says, please click this link to confirm your new email address. Now, in that email, you might put hi and then put the person's name, right? And you wouldn't usually think of adding a new email and having it confirmed as sort of a spam problem, right? But actually, this can be turned into a spam attack, and it has happened. So, right, what the attacker does is they put spam in the name, and then they add every email that they want to target to the account, and the confirmation goes out to those emails, and the email says hi, and then the spam is there. Right? So this is not a very obvious vector, right? And you wouldn't think to put a spam control around adding a new email address. So that's why it's important to figure out how to get spam out of name fields. So this is sort of a summary of direct versus indirect spam channels. So in the case of direct spam, right, those are obvious places to put spam controls. Put things like report spam buttons or have automated or manual review of content. Right? And there's typically more text to analyze, paragraphs, sentences. Where, as opposed to indirect channels, often you don't recognize it as a source of spam sort of until it happens. Right? And because there are words and short phrases, often there's not enough text for most of the classifiers. So now I'm going to turn it over to Sayan, who's going to talk about one of our name scoring models. Yeah, that one. Yeah.
Okay. Thanks, Ted. So LinkedIn's terms of service states that the user got to use their real name while signing up on LinkedIn. But not everybody follows the rule, right? So what we have is to identify such bad names at scale, a knife-based classifier that actually detects a bad name. So how do we do it? The n-gram of characters from the name is actually a feature. For example, in the name Sayan Dasgupta, the 3-gram features will look like SA, SAYA, AYA, blah, blah, blah. Now, you can see that there are phantom characters to identify that these particular n-gram appears at the beginning of the word, or to signify a particular n-gram appears at the end of the word. Now, the idea is, now if you simplify the Bayes theorem, it is actually, if you simplify the Bayes theorem, it actually simplifies to that the log odds of the posterior is equal to log odds of the prior plus ratio of this log odds for each of the features. What it essentially tells you that a particular n-gram, it's comparing that a particular n-gram, how much it appears in a spam classes and how much it appears in non-spam name. I'll explain it in the next slide. For example, based on the training data, right, theta wi is estimated as nwi by ny. So number of occurrences of that feature in a particular class by total number of elements in that class. Now, for example, this n-gram xyz appears, say, in the 5% of names and, say, 0.1% of non-spam names, right? Then it is 50 times more likely to appear in spam than non-spam. So if a particular name has more such n-grams that are more likely to appear in spammy names, then Bayes theorem will tell you that, okay, it has a more likelihood to be classified as bad. Right? But the problem is while scoring, you will come across n-grams that you have never seen before in your training set. Now, for example, here in this particular name, this n-gram, 3-gram LSE and QWE, we haven't seen that in training set. So how do we deal with that? Now, one thing is to ignore the missing feature, basically use the class priors, right? So second thing what we do is you split up the training set into two halves. One is, so for example, here we have split it into two halves, A and B. For features, say, W or Z, it is exactly present in one of the partitions, but not present in other partitions. So we aggregate, and this counts in the brackets are number of times it appeared in a good name versus number of times it appeared in a bad name. Now, so when you aggregate these missing features and you estimate for one missing feature, right? So whenever you come across a missing feature, you replace it with this value, missing feature. So this is this is definitely does better thing than ignoring the missing features. Now, the third option that you have is to do it recursively. Suppose you are using a 5-gram as your feature, right? So what you can do is you come down. So for example, here in LSE, LSE is absent, right? So we go down to LS and LSE. So eventually, you are basically recursively coming down to find the n-gram value that you actually have in your training set. So, but this is computationally, heavy, right? So we have one heavyweight algorithm and we have a lightweight algorithm. And in the next slide, we'll compare their performance. So first let us not look at the dashed lines. Let us, okay. So one is the full algorithm and one is the lightweight algorithm. This is a precision recall curve. And we see that the full algorithm is performing better than when compared with the lightweight algorithm. Now, while evaluating, what we found that, in a number of cases, what we found as false positives were not actually false positives. They were just labeled as bad names. They were not labeled as bad names. They were actually bad names. So we corrected for that, and then we again re-evaluated, and this is a dashed line. A precision recall curve will give you that number. Okay. Now, the question is, what do we do after we detect that you have a bad name, right? So what we do is, like, we ask the member to update their name. So either you can update their name, or if you think that, okay, it's a true false positive, you can just write to our customer support and get you validated. Now, so how the user experience has been, right? The best thing is that, in a lot of cases, users didn't realize that they have they have put in some typos, or they have put in their contact information. So they doesn't realize that, there is a problem with their name. Basically, they are not malicious, right? So this has helped them. This is a low friction way to correct the problem for them. And it don't lock them out of their account. And for us, it's helpful because it reduces number of contacts to the customer service. Right? So what's the high-level summary of name scoring model? So the best thing about the name scoring model is that it is language agnostic. Right? Then another thing is that it catches never seen before spams. Like 54% of the members caught with bad names have unique first names, and 47% have unique last names that we have identified. Now, given the success of the name scoring algorithm, we extended this to the headline scoring algorithm. A headline in LinkedIn is basically by default your latest designation at latest company, but you can put in spam there. So we extended this model to to headline also. Now, we have a paper published at the ISEC conference. For more technical details, you can go and take a look, have a look. Thanks.
Okay, so another technique that we use to detect fake names is something that's actually been discussed quite a bit in previous talks, which is to cluster groups of accounts that look like they were created by a single entity, right? And typically, what you'll find is that if somebody needs to generate a lot of accounts, right? In order to create accounts, they have to generate lots of names and lots of emails, and if they generate it from, say, a randomly generated list of names, then any individual name that you look at is probably going to look okay just because the name is actually a real name. But when you look at it in aggregate, there seems to be something wrong with the distribution. And I'll show you an example on the next slide. So if you look at this group of names here, they're kind of rare names, but if you looked at any one of them in isolation, it's just plausible enough that this is a real person, right? But if these are all the accounts, and then many more like this created from a single IP, then it's not as plausible, right? In a legit case, you would have many more common names within the bunch of rare names as well. So we built a model to cluster groups of accounts together. We used a random forest model, which is the model builds a number of decision trees, which are then combined into a final decision. And the features are obtained by aggregating data within each group. So known patterns in names and emails. We have frequencies of names among good users, and duplicates and other simpler things like that. And at the bottom, we have a couple of precision recall points for the model. That's all we had for today. So Thank you.
Questions?
For your n grant, how do you determine n, and what value do you currently use?
So, for the heavyweight, you can vary it from 5, 4, 3, the value of n, and find out your optimal n for that, based on your choice of accuracy measure.
For the heavyweight algorithm, we use
n
equals to 5, and the lightweight n equals 3.
How about just scraping Facebook data and just use the real people's name?
Sorry, I didn't. Can you repeat that?
To use census data or babyname.com, just go there and make your John Lees.
You're saying, sorry, go to some list of name sources and then do what?
Known names, yes.
Right, and then what about that? I didn't catch the rest of your question.
Why don't bad guys just use those names?
Well, they do, right? But they have to get sort of the frequencies right, otherwise it doesn't. Right? If you use only common names, that's also not right either, because any large batch of accounts will also have people with rare names, right? So you see people doing both. You see people doing what I showed you. You also see groups of accounts where it's only the names. They're all very common names. That's also not good.
Thank you for your talk. Question about your idea for filling missing values. If I understand correctly, you start with some n-gram, and if it doesn't exist, you go with smaller n-grams until it exists.
Right.
So it relies on the assumption that all the characters exist in your training. So,
yeah.
So how do you deal with Unicode? Do you flatten it? And if you do you do it at the beginning or at the end when you get to the character?
Sorry, can you repeat the question?
With Unicode characters, the chance that you see all of them in your training set is low. So do you flatten Unicode names, or let's say a name has Unicode characters in it. How do you make sure that all of them appear in your data set?
We discussed the missing value techniques. Okay.
So do you flatten names to only ASCII characters?
No, we.
You're saying how do you? I guess I didn't follow. What do you mean? How do you make sure they all appear in your data set? Why do they need to?
So at the end you get to just one characters, right? Then you recursively go down.
Right. So if you get to one character and it still doesn't appear, then you have to go to one of the other methods, right?
I think I can. I think I can address the question. Basically, the training set is large enough so that every Unicode character appears. We can train on the entire corpus of LinkedIn accounts.
So a quick question about the training your model. So where and how do you get the labeled data for the names, especially for the bad names?
Our security team has some of the names. Some of them are manually labeled.
Right. So we've got accounts are caught. Usually the bad accounts get caught eventually for some reason, right? So then the historical, based on historical data, we look at accounts that we've restricted, basically. We've already banned, and those are our labels. It's not perfect because accounts get banned for various reasons.
Okay, a follow-up question is, for the bad account, to maybe have a normal name, very legitimate name, do you differentiate that out?
Right, so that's, so you're saying some some bad accounts may have a real name.
Exactly.
That's true, that can happen. But there's...
So we have different models for that, catching that.
For the account aggregation, do you usually have false positive proxy IPs or the net IPs of large corporations?
Yes, that is one of the issues that we do run into. That's why. So depending on, we're working on additional models to try to look for cases like IPs, institutions that create, that use one IP and create many accounts. That's relatively rare because usually you don't have, unless it's a special situation, you don't have large numbers of people registering for LinkedIn at the same time from one company, unless it's a special event or some special situation.
Cool. If no more questions, thank you so much, Ted and Sayan.
Thank you.